Hey everyone, we are going to continue using the Manning's equation circular channel workbook, and in our previous exercise we entered the equations for Manning's n. We learned about data validation, we learned about how to use the if function, so if you change the units here, the labels change, and also when you calculate this equation for alpha, it uses one of two different formulas depending on the relative value of y versus r. And so now that it's done, we're going to explore another feature, and that has to do with how this particular equation is used in design. So if I'm an engineer and I'm designing, for example, a storm drain, generally I'm working with a predefined slope. I mean, you can't normally change the slope because you're limited by the geometry of the surface of the earth, right? I mean, that's given to you. And you're also typically given a design value for Q. You do a hydrological analysis and you say, okay, we need to pass through 50 cubic feet of water per second. And so your job as an engineer is to design, is to build a channel that is large enough to hold that. So what I'm trying to say here is it's not too common that you're given everything but Q and all you have to do is solve for Q. Typically, you're given Q and you really need to solve for the diameter. And assuming the channel is flowing 90% full or 3/4 full or something like that. And so say, okay, great, let's just solve these equations for R. Well, you can't. Solving these equations for R so that you can plug in Q, it's difficult if not impossible. And so how do you do this? Well, one of the ways you can do it is you could manually use trial and error. So I could say, well, I need to have a flow rate or a channel big enough to handle 30 or let's say 25 cubic meters of water, and we're going to assume it's maybe 80% full. So I could say, well, this is equal to 0.8 times the diameter, and it gives me 19.2. So really what I need to do now is I need to change the radius until Q is equal to 25. So I can say, well, at about 3, that's way too big. 2.5, 2.2, well, that's a pretty good guess. 2.2 gets me really close, but what I'm doing there is I'm manually entering a series of values until another cell, reaches some predefined value. It's called trial and error, and that works pretty well. But it turns out there are a lot of cases where it's really convenient to automate that process. And so a good way to automate that is to use the goal seek command, and that's over here in the data menu in the what if analysis section. If we select goal seek, it says set cell to value by changing cell. It's really easy to use. So I'm going to say I'm going to select this cell Q, B15. So it says set cell B15 to 25 by changing which cell. And again, whenever you see this little symbol off to the right of an input value, that means you can just click on a cell to designate it. So we're going to change the radius. So set the Q to 25 by changing the radius. And by the way, you can actually just enter, I'm pretty sure you can do this. Let me try it, RAD. You can just enter the actual names and it works as well. So if I click OK, you'll see it runs for a second and it gives us an actual value, which is 2.198622 blah blah blah. And so it almost instantly goes in and iterates that for you until you get the correct, or you get a value that is equal to your target value. Works out great. And so you could do this in other ways as well. You could solve for the slope if you wanted to. You don't normally do that, but you theoretically could. You could solve for roughness coefficient, and any one of the input values can be changed to make Q achieve a certain value. Now, as we're doing this, I'm going to go back. I'm going to change the diameter back. Let's change the radius back to 2. And let's change the depth back to 3 or something, so we're not using a formula. And as you look at this particular problem, an interesting question arises. At what depth of flow do you get the maximum Q? Now, you might think it's full, and let's test that. So I'm going to say 3.8. We have 21. 3.9, we have 21. And 4.0, we have 19.8. So as the depth got fuller, higher and higher, as the channel got more full, the flow rate actually went down. Now that might seem counterintuitive, but what happens is, as this depth y goes up, you're only slightly increasing the area, but you're greatly increasing the wetted perimeter. And that causes some changes to your hydraulic radius. It basically means more of the water is in contact with the surface, and that causes friction, which slows things down. So a really interesting question now is, at what depth do we get the maximum flow rate? Now once again, you could manually tweak that depth y up and down and just monitor the Q value visually until you found what appears to be the maximum. Or you could automate that. Now we can't automate this with GoalSeek, because GoalSeek, you're changing the inputs until the output matches an exact value. So what we're going to use here is called the solver. And the solver is an add-in. Now there's something we need to do in order to get access to the solver, and that is, you need to go into the File menu and go down to Options and go to Add-ins, and down at the bottom we want to do Excel Add-ins and do Go, and then you want to turn on the solver add-in. By the way, each of these steps is listed in the chapter on GoalSeek and Solver in the Excel VBA primer. And so we turn that on, and now you'll see in the data menu we have a new option that pops up here in the Analyze section. And if you click on Solver, this great little tool pops up. And by the way, you can use the solver exactly like you use GoalSeek. So you tell it to set an objective, which in this case would be Q, B15, to a value of 25 by changing cell. And anyway, so you could, if you input the Y or whatever and then click Solve, it will iterate exactly the same way as GoalSeek. But we want to do something else. We want to use it to calculate a max. So we want to set the objective is Q is the equation for Q, B15. We want to set that to a max value by changing which cells. Now you can actually list multiple cells here separated by commas, but we're just going to list one. We're going to list the depth Y. And by the way, once again, if you want to, you can just enter the cell names here. Maximize Q by changing Y. You can also add constraints. So you can say Y is less than or equal to D, and Y is greater than or equal to 0. So that just that adds some constraints here, so that when it starts moving Y around to different values, it doesn't blow up on you. And then there you can pick your optimization algorithm, which is beyond the scope of this discussion. And when we're ready, we just click solve, and we found a solution, so we'll say OK, and the solution is 21.37. You can actually expand that out if you want to a few more digits. And so 21.37. So if I go, you know, or excuse me, that's the maximum Q, but the depth corresponding to that is 3.75. So if I do 3.7, whoops, I got to do it like this, 3.7. That goes down a little bit, and if I do 3.8, it's down a little bit. And if I go back to 3.75, and I have my maximum value, so it very quickly found our maximum value. The solver is fantastic. If you're an engineer and you want to optimize your design of something, the solver is a fantastic way to set up a set of constraints and have it you know, manually iterate on your input variables until something is maximized or minimized. And it's something that's used very widely in industry and practice, and a great tool to have in your arsenal, along with GoalSeek. Both GoalSeek and Solver are really, really useful utilities to have as you build Excel worksheets.